Let's get into the concept of reversible steady flow work. Okay, that um, recall that reversible boundary work associated with a closed system can be expressed as the following. We integrate the pressure over the volume. Now, the energy balance for a steady flow device undergoing an internal reversible process can be expressed in differential form as follows. So if we take that expression, and if we recall that reversible heat transfer can be expressed as TDS, and TDS can be further expanded by one of the TDS relationships, we can combine all these expressions through some algebra to get down to the following form, where reversible work is equal to nu dP plus potential and kinetic energy. Now, if we go ahead and we take that, and if we integrate it, that expression becomes the integral of nu dP minus delta Ke and Pe. Now, to avoid a negative sign, we can rewrite the expression in terms of work in, and we end up with the same expression, but with positive quantity since it's work in instead of work out. Now, in order to be able to to evaluate this expression, I need to know nu as a function of pressure. And as we know, when a fluid is incompressible, nu is constant. So that expression is simply evaluated as nu delta P, since nu is constant. If we integrate it over to pressure, it just becomes an integration of a constant. So this expression is what we would call the reversible work in for an incompressible substance, reversible work. Now, for a steady flow device of a liquid through a device that has no work interaction, right, that work interaction is zero. So the expression results in just nu delta P plus delta Ke plus delta Pe. Now, this expression is used heavily in fluid mechanics. It's called the Bernoulli equation. And the expression implies basically that a larger specific volume, the larger the work needed to move the device, the larger the reversible work produced or consumed by the steady flow device. If the steady flow device has no work, this would be the expression used in order to be able to look at fluid flow with no work. And again, this is Bernoulli's equation. But going back to the reversible work in, is basically saying the larger the specific volume of the fluid, the larger the work needed to move the fluid, right, to pressurize the fluid. And again, that would be reversible work for a steady flow device of an incompressible fluid. Now, what about for a compressible fluid, right? Which would be basically compressors. Incompressible fluids are pressurized in pumps, and compressors are used to pressurize gases, right? So if we go back, we get the reversible work is nu dP. Now, in a special case of an isentropic process, right, that expression ends up getting evaluated as a function of the temperature in and out, as well as a specific heat ratio. Excuse me. And for isothermal process, as we went over in earlier chapters, it can be evaluated as a function of temperature and pressure. And if it's a polytropic, we just replace this K with the value with the parameter N. So basically for compressor work, you can see that if I were to look at a PV diagram, right, pressure on the y-axis, volume on the x-axis, increase in the pressure from this value to that value. If I were to actually go ahead and plot those paths, plot those equations, you can see which equation is yields the greatest amount of work, right? The amount of work is a function of the area underneath the curve. So each one is compressing the air, but during a different process, resulting in a different amount of work, where the isentropic work is called the minimum work. So why are isentropic processes of steady flow devices important? Well, the more closely an actual process approximates an idealized isentropic process, the more efficient the device is, right? An isentropic process represents a process that occurs that results in no entropy production. Since it results in no entropy production, and it will basically means that that process is occurring at the most efficient possible way. An isentropic process is representation of a process that is adiabatic and isentropic, which means that the entropy, the value of the entropy, that property entropy entering, is the same as it is exiting, right? So as the device is going in, right, I have mass times S2 minus S1 to calculate my entropy change. Isentropic means the entropy on one side is equal to the entropy on the other side, meaning if I, for example, if I have a compressor or a pump or a turbine, let's call this a pump, the entropy going in is equal to the entropy going out for the mass flow, right? So the mass flow going in has a certain specific entropy value. That entropy leaving also has the same specific entropy value. If this value S2 were to be greater, basically if the entropy coming out is greater than the entropy going in, the process is regarded as non-isentropic and less efficient. So the entropy in this case is a quantity that's used to quantify the process, to quantify the efficiency of the process, right? So let's look at the example of a turbine. So here I have enthalpy on the y-axis and entropy on the x-axis. We're going to look at the isentropic efficiency of a turbine. So this is a superheated vapor region. So pretend that we looked at saturation curve here, right? And this is a constant pressure line, right? This is compressed liquid, this is saturated mixture, and this is superheated vapor. Let's pretend we went ahead, honed in on this specific portion of the graph and blew it up here, right? So this is a constant pressure line, like this is a constant pressure line, and this is a constant pressure line as well. So we have the turbine with the steam going into the turbine state 1, and then the steam expands in the turbine and comes out at the lower pressure line, right? This graph has enthalpy on the y-axis and it has entropy on the x-axis. If you remember, for a turbine, if I'm going to do this in specific terms, if I were to do a first law analysis on a turbine, I would get that the work coming out of a turbine is equal to the enthalpy in minus the enthalpy out, times mass flow rate. But if I'm just looking at this in terms of a specific terms, right, per mass basis, it would be H1 minus H2. So if I have my turbine has work coming out, it has mass flow in, and it has mass flow out. That mass flow has a certain enthalpy going in, and it has a certain entropy going in. That mass flow has a certain is coming out, has a certain enthalpy coming out, and has a certain entropy coming out. If the entropy coming out is greater than the entropy going in, the enthalpy going out is less than the enthalpy going in, making this number, the work, smaller. Right? Again, if the entropy going out is greater than the entropy going in, the enthalpy going out is less than the enthalpy going in. The closer the entropy is to going in and going out, H2 will be maximized, meaning I have the greatest delta H resulting in the greatest work. When the enthalpy coming out is less than what it could be at a maximum value coming out, I'm wasting work to overcome irreversibility. So let's look at it in terms of this chart. I have enthalpy in a state 1, right? If I have an isentropic process, meaning a process of which the entropy is not changing going in and out, this would be represented by a straight line. And I come out at a value of H2 that I call H2S. H2S is a value that represents the enthalpy coming out of the turbine if the process were isentropic. Now, the actual enthalpy coming out will result in some increase in S, right? If I had to go further over to the right that I go, the more increase in entropy I have. So if my entropy coming out is greater than the entropy going in, it results in me coming out a little higher up, right? This is a constant pressure line. So all the pressure values on this line are the same, but if I were to produce some entropy, my enthalpy coming out, my H2 actual, A is the actual enthalpy coming out, is less than the H2 isentropic. So basically the efficiency of a turbine is going to be the actual work coming out over the isentropic work coming out, or actual work would be the enthalpy in minus the enthalpy actually coming out divided by the enthalpy in minus the enthalpy coming out if the process were isentropic. That is the definition of the isentropic efficiency of a turbine. So the more efficient it is, the higher the lower the enthalpy coming out would be, resulting in a greater work. But since the actual work is less than the isentropic work, that ratio of the two gives you how efficient your turbine is operating, or meaning how much work you're getting versus how much work you actually could get if it were 100% efficient. That's for a turbine. Now let's look at a skip ahead here to the efficiency of a pump, right, or a compressor. The efficiency of a compressor is just the opposite, right? If you think about it, a pump is a work-consuming device. So you're actually consuming work, right? So a pump is a work-consuming device. So you're putting work in to increase the pressure of a liquid flowing through it, right? So you have an enthalpy entering and you have an enthalpy exiting. You have an entropy entering and an entropy exiting. So the more irreversible your pump is, the more work you have to put into the pump to get the same pressure difference, right? So we would call the isentropic work of a pump is the same thing as the minimum work for a pump. That would be the enthalpy going in, the enthalpy coming out if it were isentropic minus the enthalpy going in. Let's go back and look at this. So here we have, again, two pressure lines. This would be in the compressed liquid region, right? So here's a saturation curve. Here's a constant pressure line. We're basically honing in on this side of the graph and blowing it up here. We have enthalpy on the y-axis, and we have entropy on the x-axis. Here we have enthalpy going in. If it were isentropic, it would be a straight line, and this is enthalpy coming out. So this would result, Ws, in the minimum enthalpy change, where enthalpy coming out is at a minimum. But if it were isentropic, if it were non-isentropic, where I would produce entropy, my outlet state would be over to the right. I'd have to come up higher on the same pressure line, which means that my enthalpy actual coming out is greater than my enthalpy isentropic, meaning that this extra amount of work was necessary to put into it in order to get the same effect because of the irreversibilities. So when you look at a pump or a compressor at that, it's going to be the isentropic work over the actual work, because the actual work is going to be greater. So in that case, I would get H2 isentropic minus H1 over H2 actual minus H1. Now, that's for both the compressor and a pump, or a pump and a compressor. Now, for the special case of a pump, I want to go ahead and show you that there's another way you can quantify isentropic work. So we're going to look at a pump, right? This is for a pump for liquid water. And we're going to look at the isentropic process. Right, we all know that for a pump, the work in is going to equal H2 minus H1. That's in per mass terms. If I do a first law analysis on a pump or a compressor, this is what I get, that the work in is going to equal the enthalpy coming out minus the enthalpy going in. Now, if you look earlier at the TDS relationships, we found out one of the TDS relationships is TDS is equal to DH minus nu dP. That's one of the relationships we went over earlier. So I want to be able to use this TDS relationship to derive an equation to find the minimum work for a pump, or the isentropic work for a pump. Excuse me. So in this case, if I were to go ahead and assume it to be isentropic, that would mean the change in entropy is 0. So I get 0 is equal to dH minus nu dP. Or if I were to go ahead and bring dH onto one side of the equation, I get dH is equal to nu dP. And then integrating both of these sides of the equations from state 1 to state 2, I get that delta H is equal to nu delta P if nu is constant. That is for an incompressible fluid. This would not work for a compressor, because a compressor, this is for an incompressible fluid. Because if I were to go ahead and use a gas is compressible. Therefore, this assumption would be violated. Therefore, this integral would have to come up with some integral form of volume over pressure. But nu is relatively constant for a liquid. I'll go ahead and write that out to make sure this is clear. Nu is relatively constant. It's relatively constant for liquid water. So that basically means that for an isentropic process, I can approximate the change in enthalpy as nu delta P for only a pump. This would not work for a compressor. So therefore, the work in isentropic, or work minimum, or just work S as we've been labeling it, equals specific volume times the change in pressure. This is, oops, sorry, my writing sometimes is not the best. This is not valid for a compressor. So, in the case of a pump with an incompressible fluid, we can go ahead and assume the isentropic work is equal to H2S minus H1, or nu delta P. They give you the same answer. So you can approximate the efficiency to be nu delta P over the actual enthalpy change. Now, this is only for the isentropic process, nu delta P. That is not for the actual process. The last device we'll talk about is the isentropic efficiency of nozzles. So the definition of the isentropic efficiency of a nozzle would be the ratio of the actual kinetic energy of the fluid at the nozzle inlet to the kinetic energy value at the exit of an isentropic nozzle for the same inlet state and exit pressure. So basically it means that the efficiency of a nozzle would be the actual KE at exit divided by the isentropic KE at the exit. Okay, I hope that's clear. I'm going to go ahead and stop here.